Good morning, class. We are back again, live, at least I'm live, from my house. And I hope that the last lesson uploaded well and you were able to watch that. And we're going to try the same thing again here with Chapter 12, Lesson 4. Chapter 12 is on circles, and Lesson 4, we move from talking about the central angles and the central arcs that we talked about in the last lesson to inscribed angles and inscribed arcs. And so let me talk you through those things a little bit. So again, first of all, we'll start with the circle. And our circle has a center, and we'll call it O. It's kind of our typical name for the center of a circle. And when we talked about our central angles, where was their vertex? The vertex of a central angle is always at the center of a circle. And so that's why they have their name, central, center. All right, inscribed angles, however, do not have their vertex at the center of the circle. They have their vertex on the circle. So if I have a point here, let's call it A, and lines, or let's call them rays, that proceed outward from there that intersect the circle at B and C. This makes an inscribed angle. Angle A here is an inscribed angle because its vertex is on the circle. All right, so A is an inscribed angle. When I say its vertex is on the circle, remember that means that it's on this line that I have drawn here. It's not somewhere in here inside of the circle, but it's right on that line of the circle. That is that's point A, and that's what makes an inscribed angle, is when its vertex is on the circle. Now the other big vocabulary here is that we see that angle A, this inscribed angle, cuts off an arc, right? It cuts off arc BC, and again we can put our little half moon shape over the top of BC to indicate that that's an arc that we're referring to. Arc BC is what we call an intercepted arc. Or we say that angle A intercepts arc BC. That's the angle that, or that's the arc that is formed in between those rays that are cut off by angle A. So angle A is an inscribed angle, BC is its intercepted arc. We can also say that arc BAC, that major arc around, is the inscribed arc. That's not a term that we use as much, but that is the correct term for that. That is the inscribed arc. Arc BAC. And if you notice, the intercepted arc, arc BC, and the inscribed arc, arc BAC, when you add those together, you end up with the whole circle. All right, so how big is an inscribed angle in relation to its intercepted arc? That's the big question of this lesson. And if I drew here the central angle that corresponds to arc BC, so if I drew this angle here, you could see that this angle, angle BOC, that central angle, is much bigger than angle BAC, right? This one is clearly more than 90 degrees. This one is clearly less than 90 degrees. What is their relationship? That's what we want to answer. The theorem for this chapter tells us, or this lesson tells us, that an inscribed angle is equal to half the measure of its intercepted arc. So we are going to prove that in the set 1 exercises, which we'll do in a couple minutes. But right now, let me just repeat that for you. An inscribed angle is equal to half the measure of its intercepted arc. So let's say approximately, how big is this angle? Angle BOC. It might be 100 degrees, right? It's bigger than 90 degrees, but it's not a lot bigger. It might be as big as 120 degrees. Let's call it 110 degrees, just for argument's sake. If that's 110 degrees, then how big is arc BC? If the central angle is 110 degrees, then arc BC would also be 110 degrees. And what our theorem tells us is that the intercepted arc, the inscribed angle is half the measure of its intercepted arc. So what's half of 110? 55, good. So the inscribed angle then would have to be 55 degrees, equals 55 degrees. That's according to the theorem, which we will prove in a few minutes. There are a couple of corollaries that come out of that, and these are pretty useful. So the corollaries say, if you look in your book, the first corollary says that inscribed angles that intersect the same arc are equal. So let's look at what that means. Inscribed angles that intercept the same arc are equal. So I'm going to erase some of these extraneous parts that I've got here. So our diagram's a little bit easier to see. So kind of back to the more original picture where we have the one intercepted arc BC and our angle A, which is inscribed. Now, it's still point O here in the center, or circle O. If I choose another point on the circle, we'll call it D, but I intercept the same arc. If I still intercept arc BC, see that? Then the corollary tells us that angle D is the same size as angle A. That could be convenient or helpful sometimes. And then we can choose another point. It could be really close to one of those points. It could be right here. We'll call that point E. If I have point E and it intercepts that same arc BC, then because it intercepts the same arc and an inscribed angle is equal to half the size of the intercepted arc, then angle E also equals angle A and angle D. All right, that's the first corollary. The second corollary says that an angle inscribed in a semicircle is a right angle. So, how big is a semicircle? 180 degrees. Good. So, again, we'll have this be my semicircle and circle O. Any angle that cuts off, here, let me say this is AB here. If I have angle C here that cuts off a semicircle, intercepts a semicircle, if this is 180 degrees, and an inscribed angle is half the intercepted arc, then that means this is a 90-degree angle. And so I will just indicate there that that's a right angle. So any angle inscribed in a semicircle is a right angle. All right, if you turn with me in your books to page 506, we will go through some of these set 1 problems together. We might be able to get through all of them, we'll see. All right, first of all, we've got a skeet range. I have never been to a skeet range, but I think they look kind of interesting. might be interested in doing it sometime. I wouldn't be surprised if some of you have been to a skeet range before. All right, so we were looking down at a skeet range. If you look at that diagram, kind of in the middle of the first column, and there are people shooting stations at A, B, C, D, E, F, and G, and we've got a circle O, and H is centered on chord A, G. And we've got some rays shooting out from A through X and from G across the circle through Y. So number 1, given that angle A equals 16.5 degrees, find angle G. All right, if angle A is 16.5 degrees, how big is angle G? Well, what do you think? The answer is the same. It is 16.5 degrees because those angles are all equally spaced. All right, so number 2, find the measure of angle AOG. All right, angle AOG, how big is it? Well, it is going to be 180 degrees. So if we just look at that triangle first, triangle OAG, look at that triangle there. If the angle at A is 16.5 and the angle at G is 16.5, then the angle at O is going to be 180 degrees minus 16.5 minus 16.5, or 147 degrees. Number 3, given that the 6 arcs between points A through G have equal measures, find the measure of each arc. So how big is each of those arcs? So I have 147 degrees at this measure here, right? 147 degrees. And then I've got these points, B, C, D, E, F, G. So how many arcs do I have here? I have 1, 2, 3, 4, 5, 6 different arcs, and 147 divided by 6, 147, that's the measure of that central angle, divided by 6 is 24.5 degrees. You can punch that into your calculator if you need to. Okay, the clay pigeons are released in the directions AX and GY. So those are indicated by those red rays there. And the shooters are trying to shoot those clay pigeons as they're released. So number 4, find the measure of arc GX and the measure of arc AY. Well, if I look at my diagram there, you see that angle A is what kind of an angle? It is an inscribed angle, which is what we're talking about in this lesson. And we know that it is 16.5 degrees. The inscribed angle is equal in measure to half the measure of the intercepted arc. So if angle A is 16.5 degrees, then the intercepted arc, which is XG, is how big? It's going to be twice that size, and it's going to be 33 degrees then. Number 5, find the measure of arc YX. Well, this is going to be, there are a couple ways you could do this. Probably the simplest way of doing this is recognizing that that angle at O, which I have kind of drawn up here for angle AOG, is a vertical angle with angle YOX. And because vertical angles are equal, that angle YOX has to be 147 degrees also, just like this angle here was on the bottom part of O. And so the measure of arc YX is going to be equal to the measure of its central angle, which is 147 degrees. So arc YX is 147 degrees. Theorem 63. Complete the following proof of Theorem 63 by giving the reasons. So we are given that angle P is inscribed in circle O, and we want to prove that angle P equals half of that intercepted arc. I'm going to go ahead and draw the picture up here so that we can follow along a little more easily. So I've got circle O, I have point P over here, and it intercepts arc AB. All right. We're going to prove this in two different parts, part 1 and part 2. In the first part, we're looking at where one of these rays goes through the center of the circle, and then we'll look at a case where it does not go through the center of the circle. All right, so number 6, draw OA. Why can I draw OA? That is because 2 points determine a line. What part of a circle is OA? That's a radius. That will come into play here in the next problem. So OP equals OA. Why is that true? Because all radii of a circle are equal. What else does that mean those equal? Yeah, it also equals OB. Not going to be super important to us in this proof, but it is true, and it's good to recognize. All right, number 8, angle PAO equals angle P. Why are those two angles equal? Those angles are equal because in a triangle, the angles opposite equal sides are equal. So we have an isosceles triangle there. Two sides are equal, so the angles opposite them are also equal. Number 9, angle P plus angle PAO equals angle AOB. So this angle plus this angle equals this angle out here. Why is that true? What is the relationship of angle AOB to